It's more a theoretical talk I'm going to give, so it's not that concrete. I'm not talking about elevators, forgive me, but being the architect and engineer of this tower here, which you have been visiting today, I will give you some background information of the tower too. We come to that at mid-span of my talk. I'm reporting today what we are doing in our university institute, the Institute for Lightweight Structures and Conceptual Design, the ILEC, or as we call it in Germany, the ILEC, at the University of Stuttgart, and I will add a few comments of buildings we are doing. We dedicated our entire scientific life to lightweight, means the minimization of material. At the very beginning, we did so in the early 70s and 80s because this was the most complicated thing you can ever do. Working with lightweight structures means you have to work with optimality, with minimization. Typically, everything is non-linear, and even the geometry is so complicated that you had difficulties to describe it at the early 80s when I was a student. In the meantime, the necessity to build light, to use less material, dramatically changed. It is not the top complex and top interesting part of the science of structural engineering. It is a need to survive for our population, for our society. Every German citizen owns 490 tons of building material. 50% is about above ground and 50% is infrastructure. The so-called industrialized countries in the world, every citizen owns 335 tons of building material. Average in the world, everyone owns 110 tons. Now population growth net is 2.6 person per second. Means if you want to donate or give or allow them a German building standard, you would need to produce per second, day and night and all over the weekends, 1,300 tons of building material. If you would do it on a lower level, let's say the level of the industrialized countries, it is still more than 900 tons per second. If you do a material flow analysis, which nobody obviously did before we came up with that question, the answer is relatively simple: it does not work. There is no chance to dream of a tomorrow, as we see it in most of the architectural sketches and sceneries of how we are going to live tomorrow. There is no way. We are running out of zinc, we are running out of plenty other materials, we are running out of sand. So within a few years, we came to the position that lightweight is a need to survive and a need to stabilize our social configurations on the planet. So we see now lightweight structures from another perspective. When I was young, building light was a necessity when it came to building high or to bridge long spans. This is the load-bearing structure of the German Pavilion 1967 in Montreal. The clear span is about 90 meters and the structural thickness is 10 millimeters. So this is already something. Lightweight was also a necessity whenever it came to moving something or flying. We designed many convertible roofs with clear spans of up to 65 meters, fully automized, etc. There, if you want to move the roof really fast, means cover or uncover 3,000 to 4,000 square meters within 3 minutes. It is about accelerating and slowing down mass, so lightweight is a need in order to survive. What did we do? A few aspects in lightweight engineering up to now. Okay, there is topology optimization and there is shape optimization. This is a wonderful example for a bridge never been built, designed by Myron Goldsmith when he visited Nervi in his Italian office in the mid-50s. So what did Myron do? He just had a beam, and on the top of the beam, which is called a bridge, where the traffic is running, there is no chance to optimize and undulate or whatever. So this thing had just to be flat. So the optimization took place on the lower part, on the lower line, and he formed the beam following the line of moments, more or less. You see the field moments, you see the negative moments above the supports. This is what he did. So we call it, this is the optimization of the exterior appearance. never anyone asked for the optimization of the interior. We just said this is a hollow box beam, or this is a massive profile, but there's another world inside. So we said, okay, from a straight beam to this, we save already 20 to 25%. From taking this as a massive beam to a beam which shows openings and cavities and hollow areas inside, which are arranged in a way that they follow the flow of forces or the structural loading of the interior, you can save another, depending on what structure we are talking about, 50 to 70%. But the complexity is dramatically increasing, because now we are in the middle of the science, mathematical science of sphere packaging and packaging other things. But if we have a set of given, for example, spheres, which is the most trivial and most simple thing, and we arrange the bigger ones and the smaller ones in a way to create within the formwork a type of foam, which we then, the cavities fill up with concrete, the result is that. Now the scientific question is, how do we group and how do we place the spheres so that these tiny struts in between the spheres follow the forces? But if we do so, and in the meantime with a couple of doctoral dissertations at our institute, we are more and more approaching those levels of interior optimality, you can save endless amount of material. And we easily can imagine to put this inside a slab, to put this inside a load-bearing wall, and to have the cavities there where the loading is low. Besides, we do that in a mono-material technology, so we are not putting any styrofoam bubbles or plastic spheres or whatever into the material, because building industry stands for 60% of the mass waste production, not only for 60% of the consumption of resources, also for 60% of the waste production. And whenever we pour concrete around a plastic sphere, no one is able later on to recycle that. And there is for every building a point when it comes to its end, as we all know. But you can imagine that if we consider this now as an interior load-bearing structure, that the complexity to calculate the flow of forces and the stress level is dramatically increasing. So we have to find methods and technology to make that usable for the everyday project and for, let's say, also for engineers not educated in the highest levels of lightweight engineering. But it is quite clear if we take such a console here, and Kraft, and a very typical German expression for force. So this force is inducing a moment loading, and typically you have a massive console there. By putting only a couple of bubbles inside to make it clear what we are creating, we create an interior truss, and wherever there is less truss loading, there are the bubbles. So saving 50% is easily to be achieved. Another thing was create an overall clever structural element, like, for example, a shell, double curved, typically a non-constant curvature. In this case, it's somehow trivial because it's a sphere, but it's the thinnest glass shell ever built in this world. It has a clear span of 8.50 meters and a thickness of 10 millimeters. We could even have driven that down to 5 millimeters, but we were a little bit anxious. So in the executed shape, which is now an element which we have in our institute's garden since 14 years, the thickness to span ratio is 1 to 850, which is the factor 20 more thin than you find it at an eggshell. And an eggshell is already considered to be something very sensitive. So super thin. By the way, there is no metal element above the equator. So it's all glued with a glue we especially developed to create something where we bring the glass panes together and where we have a load-bearing glue without any creep and without getting brittle under UV loading. But still here, where we have a constant thickness, the stress field is not constant. So we have level where the stress is higher and where the stress is getting lower. And how could we answer this? And then we switch to concrete again, because it's easy to be done in concrete. we developed a formwork technology which is based on frozen sand. So we take a certain diameter sand granulate, we spray some water on it, we freeze it, then we machine it, and then we receive a formwork, super complicated, no problem at all. You just machine it out of the frozen sand, and then you pour the concrete on it, and you achieve shell structures. This is a piece of a shell structure, where the openings are adjusted to the level of loadings. The better we got in describing the loads over the past decades, the better we got in increasing the strength of the material, the precision we got in describing the material's behavior, the increasing precision we achieved in describing the load-bearing behavior of the entire structure itself. One of the keywords might be finite element versus some hand calculation, the thinner the shells got. But if a load-bearing element, which you design as a lightweight element, gets thinner and thinner and thinner, then you are losing what we call the shape-defining load case. Yeah? In former times, the famous Heinz Isler, he designed these 35 to 40 meter spanning concrete shells, astonishing, breathtaking thin, with a thickness of 20 centimeter. Everyone was shocked at those times that you can do a concrete structure that thin. But he took advantage of the fact that the dead weight of that shell is 500 kilograms per square meter. So he said the dead weight is the dominating loading case compared to snow and wind and whatever. And he took the dominating loading case in order to form hanging models under tension, then inverted them and said, okay, this one is then under compression only. This is ideal for concrete. So this is the way he did it. But with the increasing strength of concrete, from a concrete with a strength of 25 to 30, which was applied here, to 250, which we are researching actually in our institute, this is factor 8, the thickness is decreasing. And the ability to describe the effects on the structure and the achievements in describing the behavior of the structure, we nowadays could do something like this in super high strength concrete with 2 or 3 centimeters. But this means we lost the form defining loading case, which was crucial. And then the question is, what are we doing now without this? Though there is a certain group of scientists which then came up with Pareto optimization. Pareto optimization is the middle of whatever. It is the wrong way. Because if you take 25 or 250 loading cases and you calculate certain optimum shapes for them and then you take a certain weighted average shape out of it, it is by definition a sub-optimum. So I once gave a lecture, this is already more than 15 years ago, where I did what I did actually, hit my fingers on the table, and then I said, which finger is taking what force? And everyone would say, okay, one of the 5 fingers is taking 1/5 of the weight of the arm. But if I release the muscle, 4 fingers have to take it. And if I release some muscles more in the other fingers at the very end, only 1 finger is taking the load of the arm. And then I said, okay, now we have to transfer this in load-bearing structures. If we would be able to, for example, in the most simple way, create a truss where we have a couple of diagonals or upper or lower chords or whatever, where we introduce a, let's call it actuator, very abstract, something which can increase or decrease its actual loading by whatever mechanism, then we should be able to manage the flow of forces within a given structure. If we are able to do that, then we could do the next step and say, what is now the optimum geometry and topology of a structure we do not know about how it looks like, under the given chance that we might build in some actuators. So now, this shell, again, is 500 kilogram per square meter and was considered to be a sensation. This shell is the thinnest wood shell ever built. It is 24 kilogram per square meter. It is 40 millimeters thick and has a span over the diagonal of more than 14 meters. The shell stands there under dead weight and relatively low non-symmetrical loading. As soon as a non-symmetrical loading of higher level occurs, the shell collapses, definitely. So what we did is we embedded only 14 sensors into the shell with a very, let's say, elaborated way on where to put them. And we measure in real time the deformation of the shell. And then we inter and extrapolate the deformation, and we gain the deformation field, the displacement field. And then in real time from this, we calculate the stress field. And then we calculate an anti-stress field, which is related to support displacements. And then we displace the supports, and this is the natural behavior, and this is the artificial behavior we induce, and the result is 0. So we can load this super thin shell dramatically non-symmetric by manipulating its internal stress, means also its internal deformation fields. So nobody believed that. But it happens, it works. You can see that at the institute. Here we have 4 supports, out of which 3 are movable and 1 is fixed, this one. It looks a little bit militaristic, but this is because the scientists needed directly access and monitoring options, etc., etc. If we look at a close-up, this is at every support 3 super high-speed hydraulic jacks with a precision of 0.1 millimeter. And we move the hinge over here within more or less real time up to 300 millimeters up and down. We could cause self-destroyment if we would do that in the wrong way. For regular loadings, which happen in Stuttgart, Germany, where we have the shell, the movement necessary is within a few millimeters only. So if we do, for example, a structure analysis under non-symmetric loading, this would be the stress field in the shell. Here we take a von Mises stress. We could take any stress. It's just a symbol. And the stress level here indicates collapse, dramatic collapse. Now we move the supports and we overlay the anti-stress field to the natural given one, and the result is what I call a homogenization of the stress field. We more or less drive every peak stress down to average stresses. But this means that we can save plenty of material if we are able to introduce that into our built structures and to make it somehow safely working, or to live with a reduced safety coefficient. So here, look at this dot here. Red means the manipulation is off. There is one young scientist trying with his, let's say, reduced set of muscles to move the shell. And you see how flexible the shell is. And then in green, we have the manipulation and the shell stands still. So it's also an active damping, super fast, damping the movements, the vibrations down to 0. There were, at the beginning, parallel studies where we had edge cables and where we pulled on the cables and had certain, let's say, devices here, mechanical devices, so that we introduced stresses along the free edges. But it in the meantime turned out that this is not the optimum, that the movement of the supports is, for a regular high-rise building, not the optimum either, but what we are working on is embedded actuators in, for example, concrete slabs, so that we have multicellular, textile, foam-type muscle element with high oil pressure inside, which can shrink or expand in different directions in such a way that we induce artificial stress field within our structures, saving 60 to 70% of the material. At the very, very beginning, when I was talking about this and nobody believed it, and I showed the formulas and everyone said, okay, the formulas look crazy, but we don't believe that either. So we built a model which we then called the Stuttgart Beam. This is like from the beginning of the movies. a 1.80 meter clear span, 3 millimeter thick aluminum ribbon. This is a tiny locomotive which we redesigned, an electric one, plate tool, which we redesigned to a little bit more orthogonal and made it 300 gram heavy. And now look at it. If we start the movie, locomotive goes to the other support, and due to its dead weight and the thinness of the structures, the deflection is in the range of 70 millimeters. On the way back, we manipulate the structure, and the deformation below the wheel is 0. Something impossible to be achieved in a natural structure. 0 deformation under a running wheel. How do we do that? This is quite simple. It is so trivial that everyone already found out how it works. This is a perfect hinge. This is a perfect hinge which can be moved horizontally. We measure the dead weight, the weight here, and we measure the weight here. The sum of the two forces we measure is the dead weight of the locomotive. The difference in the two measures we weight in is the position of the locomotive. So if we know where the position of the locomotive is, we move that support. Because this is a triangle, it induces bending in a way that the deformation is 0 below the wheel. You can't build lighter, and no one out there can build something where you have 0 deformation under a running wheel. Now we took advantage of this know-how we achieved over the last 15 years when we won the competition together with the firm of Züblin, and our office, being the architect and the engineer, we took Helmut Jahn as our support, especially for the interior and for the entrance areas. But what you see here is the first sketch or visualization we did for the ThyssenKrupp Tower. So what is important here? It is a purely functional element. It has to allow all the tests needed to be done in the upcoming decades. So it just has to work in its daily business. But due to our philosophy, it had to be minimized in the material built in. And how did we do that? 2 effects. There's a textile cladding there. The textile cladding has spiral ribbons. They are nothing else than a vortex element so that we can reduce the wind load for the tower. Then this textile covers the concrete surface. It shades the concrete surface, means it reduces the thermal stresses, which heavily influence the amount of reinforcement needed to build this reinforced concrete structure. Because typically we have on south-southwest, where the sun is with the most power and the longest time shining on this hollow box tube, a relatively high surface temperature. Inside, we have a constant temperature. On the north and east side, it's relatively cold. So the tower always tends to overlies. But when it tends to overlies, we have to counterbalance that with reinforcement. If it does not overlies because we do not allow for overheating on west-southwest, then we can save reinforcement. So we saved reinforcement because of the shading, and we saved a lot of reinforcement because of our wind turbulence manipulation. But you already know it, or I think you got the track. The main reason is because it looks better. So after we designed the concrete pipe, I said we have to throw a negligee over that. Everyone knows what a negligee is. And then we do the negligee first time in the world that high, and with a varying openness. Means here we have 10 threads per centimeter, so it's a relatively densely woven thing. You do not see the concrete pipe. The fabric is just sheer white. But as we go up, the fabric opens, and at the very end we have only 2 threads per centimeters, so you can look through if you look orthogonal onto it. When you look at the sides where we have the spiral, the cylindrical effect, the material closes again. The thing is relatively complicated, so even our great visualizations were unable to show that in the visualization. but I know how it will look like. So we just wait until October, and then we all look at the negligee. And if we draw it away from cost or from money invested for beauty, the reason I'm giving to the client is that it's highly functional. So for those who are interested, I show one of the first movies we did explaining how the tower came up. You see the slot for the panorama elevator. We all learned about the active-passive mass. The entrance areas like this, we have all been there eating and listening. Actually, the steel pipes forming the spirals are under installation, and once they are done, we start with the textiles. So this then gives you a first idea on how the openness of the textile is going to influence the architectural appearance. Now, and this is the reason why I had to undersign that I'm staying for 4 years longer at university, is we got a huge research contract in the level of close to 40 million euros to further research adaptivity in load-bearing structure and building skins. And since I was the one who came up with the idea and who is the leader of the research project, the German government said you minimum need to stay for 4 years more, otherwise you don't get the money. So I had to sign this contract 4 years more, which also means that I'm retiring at 68, but that I'm lucky to have a huge, brilliant staff, which is doing, for example, a high-rise building, like the left one, which is then restructured and rebuilt into the right one. So it is a high-rise which is under constant modification, and where we have different load-bearing structures, all equipped with adaptive elements, with actuators, where we try, not only as at the ThyssenKrupp Turm, to manipulate a lateral sway back to zero, but where we also try for different structural systems to redistribute vertical loads, maybe caused by dead weight or payload, or caused by lateral loading, in a way that we fully equilibrate the vertical loads on all the columns. That will be very interesting. Save weight, save building material. Always remember 2.6% net increase per second in the world. We transfer those ideas of adaptivity, of manipulating the deformations, also to super thin facades. This is a prototype. You can visit this in Stuttgart at our institute, where the entire facade is just held up by 2 cables with 6 millimeter diameter. Of course, the deflections are huge under wind loading. But we measure the deflections and in real time answer with these elements. This is not a movie now, I'm sorry, it does not work. Push the facade backwards, so that the facade is permanently one vertical plane. Other research at the Institute is switchable glass. Here we follow a liquid crystal technology which allows us to filter out certain frequencies of the natural light. Means you have brilliant light coming in but not infrared. Or you have the infrared going out but not the visible light, things like this. Or technologies where we place an artificial shade exactly between the sun and your face, so that you have never any glare problem, but the rest of the glass pane allows for energy coming in and illuminate the night, the room. We have elements between 2 textile layers where we collect warmth. We have what we call, this is now a geometrically meso technology between 1 and 100 millimeter diameter openings, which, if they are closed, have a relatively good thermal insulation quality. If they open, they allow for a perfect airflow. If we close them, they are wind and watertight. You can do that even more elegant without any electric engines, just with pneumatics and a layer of textiles, where we allow an adjustable breathability of the surface. Something we would love to have now, actually. Imagine we would have this, then we would sit in fresh and cool air. So this is what we are researching. This yields to a new type of architecture. because the building itself might act on your command, or it's going to act without your command, and you have to accept that, or you have to dispute with the building. So this is another part of our research. What is the human being accepting, and where is a certain borderline where it becomes too technical or even ridiculous? What makes sense? What is the future? What is definitely not the future? And how does this new architecture look like? The new building skins. So we are, as you see here at the facade, going to research that over the next 12 years, permanently replacing the facade, permanently modifying the structural system, and hopefully after 12 years we have a contribution to allow to build high-rise buildings and low-rise buildings in a way that they fit the human requirements and that they use dramatically less material, because we don't have that. Thank you.